Hello, so today's video is going to be just some more practice with epsilon-delta proofs for limits, except this time we're going to focus on quadratics and how to prove the limits for quadratics exist. So let's note down some examples, or basically we're going to do two examples, one specific and one more general, which you'll see what I mean. So the limits as x approaches, let's do 1 of x squared plus x is equal to 2, and the limit as x approaches a of x squared is equal to a squared. Okay. So first let's note down the definition of limit in general. So the limit x approaches a of f of x is equal to L. And then for this limits, the definition is for all epsilon greater than 0, there exists a delta greater than 0, such that this following implication holds, which is that the distance between x and a is greater than 0 unless delta implies that the distance between f of x and L is less than epsilon. So what this is basically saying is that you're proposing your limits, the L, and you're saying that for whatever tolerance you allow for around that L, we can always find values close to this A value such that the corresponding f of x values are within that tolerance, within around the tolerance around the proposed limit value. So this is basically saying, let me draw a graph to make this easier. This will be like here. So here's the limit. So then we're saying we can choose whatever tolerance around L, and that we can choose an appropriate delta. For example, this small delta, in order for the corresponding f of x values to always lie in between this epsilon window. And the magic here is that we can make whatever epsilon tolerance we want. So we can make it as small as we want. So then this should work for all epsilon, and then if you keep making epsilon smaller and smaller, it shows that, and then if you can always find a working delta, it shows that that limit must exist. You keep approaching that limit. This gets at the approaching behavior of a limit. So with this small review, we can get on our way. So the first example was, and actually before going to the example, I do need to talk about something called the triangular the triangular inequality, which basically says that if you have two numbers m and n in that are part of the real numbers, doesn't necessarily have to be positive, that the absolute value of m plus the absolute value of n is going to be greater than or equal to the absolute value of m and n. So this is going to be useful for a proof, which you will see, and this holds true because you're basically saying that we're basically adding the magnitudes of m and n, so then these are going to be greater than or equal to 0, greater than or equal to 0. We're basically adding essentially like positive numbers, or 0 if they're either of them are 0. And so this is going to be greater than or equal to adding them individually and then taking the absolute value, because when you add them individually, if one of them is negative, it like kind of cancels out with the other numbers. So if m is negative and n is like positive, for example, or vice versa, then they're going to kind of cancel each other out, and then you take the absolute value of that canceled out number, if you see what I mean. And then on the left, there is no canceling out because they're both going to be positive or 0 individually, and then you add them. So then it's going to be greater than or equal to that. So the left is greater than or equal to the right side. So with this, let's get on with our first example. So the limit as x approaches 1 of x squared plus x is equal to 2. So first, let's state our givens, which is that epsilon is greater than 0. Delta will hold some value that will allow for the whatever x values within this delta window that would allow for the corresponding f of x values to be within a desired tolerance from the limit. And obviously we're going to try to find this delta value within our proof. So we have that, and then we assume our hypothesis that the distance between x and 1 is greater than 0 and less than delta. And then our goal is to show that the consequence logically follows, that we get this part using our assumptions. Distance between f of x and L is less than epsilon. And again, we start with we start with kind of the beginning piece of the consequence, which is that the distance between the function and the proposed limits. So we start with this piece, and then we're going to show that this is going to be less than epsilon, and we're going to show that by using our assumptions. So let's first conduct some algebraic manipulations. So this is obviously equal to well, we would use x plus 2 and x minus 1 for this to work. And then if you distribute this out again, you're going to see that this is correct. This is equal to this. And then this is equal to x plus 2 in absolute value times x minus 1 in absolute value. And then, so we have this piece, and then we see that we know something about x minus 1 in absolute value, that it's less than delta. So then we can just plug this in. So x plus 2 in absolute value delta, and that's greater than this piece over here. Okay, so now we need to get rid of all references to x, because x is not going to be a constant value. X is really like, so delta is really the delta window encapsulates all the x values we're going to use, so we don't want it to be in terms of x. It wouldn't make sense really. So thus we would want to find a way to cancel this out. To replace this with a constant. So what we can do is that we can assume that delta is less than or equal to 1. And so we can do this because we don't need to find the optimal delta. I mean, not the optimal, the biggest delta. We just need to find a delta that works. So if we have a function here, a, l, and then our epsilon, we see that, see that using this delta window over here would be the maximum one, but we could really use like this super small delta window over here, and it'll still work because all the corresponding f of x values would still be within the epsilon tolerance. So if the maximum delta were really bigger than 1, then we can still choose one that is, we can just choose any positive delta that is less than the maximum delta. So it can be less than, it can still be less than 1, right? And then if the maximum delta were less than 1, so if we choose epsilon such that the maximum delta must be less than 1, then we would need to find another appropriate value for delta. So what this is saying is that we're really kind of limiting delta to be we're maximize, so the maximum size of delta here can just be 1. We're just assuming that. So let's go back up here and say that it is the minimum of 1, and the thing we're actually going to find out that involves epsilon. So the maximum size it can be is 1, right? Because if epsilon on n times some constant, or divided by some constant, if this happens to be bigger than 1 in some cases, then it'll just minimize it to 1. And then if this this over here happens to be less than 1, then this value will be chosen. So in all cases, the delta will be appropriate and functional. Okay. So we still need to continue on with the proof though. So assume delta is less than or equal to 1, and then with this, we know that delta is up here is less. I mean, we know that the x minus 1 in absolute value is less than delta. So then we can say that delta is less than or equal to 1 is less than, I mean, is greater than x minus 1, right? And then we can say that x minus 1 is less than 1. Just contracting this over here. And then we can say that x minus 1 plus minus 1 plus absolute value 1 is less than 1 plus absolute value 1. We're just adding absolute value 1 on both sides of the equation. Obviously this is going to just absolute value 1 just equal to 1. So it's, oh sorry, I mean it should be actually it should actually be 3, and I'll show you why. So x minus 1 plus absolute value of 3 is less than 1 plus absolute value of 3, so then it just goes to 4 is greater than x minus 1 plus absolute value of 3. And then from our reverse triangle inequality, we see that the sum of two magnitudes is greater than adding the two numbers and then getting its magnitude. So, or greater than or equal to. So then this is greater than or equal to just x minus 1 plus 3. Right, so we're using the reverse triangle inequality to compress this down into one absolute value. And that we see that the relationship between this and 4 is that 4 is greater than that number. So then with the algebraic manipulations, you can see that x plus 2 is less than 4. Okay, so that was actually a little bit of work. So now we know that x plus 2 is less than 4. So then we know that x plus 2 times delta is less than 4 delta. And then again, we want to choose a correct delta value so that 4 times that number is equal to epsilon. In order to finish off our proof, we want to show that this x squared plus x minus 2 is less than epsilon. So we would choose a delta equal to epsilon over 4 to finish our proof. And epsilon over 4. Okay, and now using all our assumptions, we have showed that the consequence holds. And so the proof for this limit is done. And we see that the delta value is the minimum between 1 and epsilon over 4. And again, we use the minimum because we assume that delta is less than or equal to 1. And then we can do that because if delta were greater than 1, a smaller delta would always work. And then if the maximum delta were less than 1, we would just resort to this epsilon over 4. So now that we finished that one, we can prove the more general case over here. Slightly more general. We could have done like ax squared plus bx plus c or whatnot, but we'll just stick with the simpler generalization. So limit as x approaches a of x squared is equal to a squared. So we start with our givens. Epsilon is greater than 0, delta is equal to some value, and distance between x and a is less than delta greater than 0. So we start with the beginning of our consequence, which is that x squared minus a squared is in absolute value, and then we're going to show that it's going to be less than epsilon. First do our algebraic manipulations, right? We're going to factor this and then split them up into their own absolute values. Then we can use the x minus a in absolute value is less than delta. So then we can replace the x minus a over here. and we're left with delta times the absolute value of x plus a. And then again, we can assume that delta is less than or equal to 1, but then just to show we can use any number, really, we can say there's less than or equal to like 3, for example. And then again, from above here, we know that delta is also greater than x minus a in absolute value. So x minus a is less than 3, and then we can add absolute value of 2a on both sides. And then from the reverse triangle inequality, we know that the right-hand side is greater than or equal to x minus a plus 2a. So x plus a is less than 3 plus 2a. So now we know that this is less than delta times 3 plus 2a. And again, we are able to put this also, we are able to set delta in terms of a as well, because we're treating a as constant. So this is the delta for now is the minimum of 3, and the other value that would be in terms of epsilon. And so what epsilon should we choose in order to convert, what value of delta uh, for delta would work to convert uh, this expression over here into epsilon? Well, obviously we would want delta to equal epsilon over 3 plus 2a. And then in order to cancel out this 3 plus 2a in absolute value. And then our proof is done with using delta value of the minimum of 3 and epsilon over 3 plus 2 absolute value a. Okay, so I hope you enjoyed this video. And then next time I'm thinking of doing higher degree polynomials, like x to the fourth, x to the fifth, and maybe even the general case, like x to the n. But I thank you for watching this video, and I hope to see you next time.